we have for our section. Again, the first thing I always do is establish a baseline. In this particular case, I identify how many sections I'm going to be working with. I have the half circle, I have the rectangle, and I have the triangle. And then I know the equation for the neutral axis is the sum of the areas times the circles divided by the sum of the areas of however many number of sections that we have. In this particular case, we have 3. So I usually, just as a personal preference, I usually start at the baseline and work my way up. So we have the area of the semicircle, so it's going to be 1/2 pi r squared. Then we need to find the distance of the centroid of this area in reference Okay, again we have beryllium with 210 moles. We have uranium 233. It was enriched to 8%. And then we have our 238, and that would be the balance of that one particular mole of fuel. So we had 210 moles of moderator versus 1 mole of fuel, of which 8% was uranium 233. First thing we need to do is calculate the volume. And we need to find the volume of each of the constituents. And basically, that is the number of moles times the atomic weight divided by the density. So for each of these, the volume of the beryllium is 210 times 9 divided by 1.82, and I had that value come out to be 1038.5. The volume of 233 is equal to 0.08 times 233 divided by 18.9. That value was 0.986. And then I have the volume of 238 is equal to 0.92 times 238, again divided by the 18.9. And that value had to come out to be 11.585. So I had my total volume equal 1051.03. I know that I can take Avogadro's number, divide that by the volume, and I will have the basis for creating the number densities for each of the materials. So this value came out to be 5.73 times 10 to the 20th. If I then multiply this number by the number of moles, I will come up with the number density for each individual one. So the number density for my beryllium is going to be 210 times 5.73 times 10 to the 20th. My number density for 233 is going to be 0.08 times 5.73 times 10 to the 20th. And then finally, my number density for 238 is going to be 0.92 times 5.73 times 10 to the 20th. Okay. Once I have those values established, in particular these values, I can go and calculate the value for transport cross-section and absorption cross-section that I need to work to find buffer. So I'm going to keep this value, but now I'm going to go and do the other. So if I look at the definition of macroscopic cross-section for transport, and we know that this is going to be for thermal, because we're only looking at thermal neutrons, this is equal to the sum of the number densities times the microscopic cross-section for scattering times 1 minus the average value of scattering in the laboratory system. We have to do this for however many number of materials we have. So this is going to go from I is equal to 1 to N. We have 3 different materials, so we're going to have to do this calculation 3 times. So if we look at doing the beryllium first, the N now is 210 times 5.73 times 10 to the 20th. The scattering value, which you get from the back of the book, is 7 barns, so 7 times 10 to the minus 24th, make our units line up. And then this turns out to be 1 minus 2 over 3 times A, which is the atomic mass. And for beryllium, that number is 9. We're going to add to that the contribution for uranium-233, which is going to be 0.08 times 5.73 times 10 to the 20th, times its scattering value, again for thermal, and that value was 8.2 barns. And then we use the same value there. Then finally we do it for the third one, which is uranium-238. This is 0.92 times 5.73 times 10 to the 20th. Its scattering value for thermal is 8.3 times 10 to the minus 24th times 1 minus 2 over 3 times 238. So when I did all of this math, I had this value come out to be 0.785. Any questions on that? All right. The next thing I needed to find out was my microscopic cross-section for absorption. And we know this is the sum of N times sigma A. I is from 1 to however many number we have. Again, we have 3 materials, 2 fuels and 1 moderator, so we're going to have to do 3 calculations. So if I look at the beryllium first, that's going to be 210 times 5.73 times 10 to the 20th. The absorption cross-section for beryllium, and again, we're only looking at thermal. That is 0.01 times 10 to the minus 24th. We then need to add to that the contribution due to 233, which is going to be 0.08 times 5.73 times 10 to the 20th times the absorption value for 233, and that value was 576. And remember, when we have used just the materials that make up our core, however many number of moderators we have, however many number of fuels that we have, and we know how to go through this progression now to find K infinity, to find volume, to define number density, to define cross-section for transport, cross-section for absorption, and then put that into thermal diffusion length squared, and then ultimately to get it into buckling. Any questions on what we did for the quiz? Okay. What I'd like to do with our remaining time today, and you can follow along with me, is I want to take this.
Before we continue, could you just clarify what the extra credit was on that quiz?
Okay. Yeah. Okay. The extra credit was, I asked you, could we determine K effective from K infinity? And the answer was we could get a good guess on that. We know that they're not the same because K effective implies that we have some type of leakage going on. K infinity being an infinite size reactor, we can. So if you look at the example on page 261. Any questions on this before I recess? if you go back to the definition of buckling squared, if you cross multiply, if you then add 1 to both sides, and we haven't really changed anything yet. If we then look at affecting this by this, if we basically divide both sides by this, we let 1 be criticality, what happens is this number that you have here, which they've shown you in that example problem, is a measure of the probability of non-leakage. So the probability, you have 2 probabilities. You have a probability of leakage, you have a probability of non-leakage. So by taking this and relating it back to just criticality, we have a measure of non-leakage. So therefore we have a measure of leakage. So if you multiply the leakage times K infinity, you would have an estimate of what K effective would be. I don't know how many of you actually took the step of trying to calculate that. If you put down something that there was the difference and what that difference meant, I'll give you credit for that. But I wanted you, if you took it the next step, you would have appreciated how they came up with that expression. When we go on...
No, I mean, I can appreciate that. I guess I just didn't read the question correctly. I mean, it says, if we only consider thermal neutron leakage, our K infinity can now be K effective.
That's correct.
So
if you account for leakage, you can. When we go further in the chapter, this was non-leakage for thermal neutrons. We're going to come up with a probability of non-leakage for epithermal and fast neutrons. So remember, everything we're doing so far is only for thermal neutrons. And when we have thermal neutrons, we call that one group theory. If we go up to include 2 groups, we're going to have still leakage for thermal. We're going to have leakage for, if we lump them all together, just say epithermal and fast. The more groupings that you have, you'll have leakage out of each group. And I think I mentioned the other day that for a typical commercial reactor, they use 17 group theory. So they're coming up with sets of equations to cover what is going on for each section. You design your fuel to optimize scattering, minimize leakage going down. And they figure with 17 groups, they can assess what is happening. And what you actually come up with when you do that let's say we have 17 groups. So you have your first group here, which is thermal, and then you have the remaining other groups to come up. The very first one is going to be fast. And again, whenever you have something and you're looking to see what goes on, you're looking at the change in neutron population with respect to time. That is always production minus loss. In this particular case, the production only comes from the thermal fissioning of a thermal fuel. For losses, we can have absorption, we can have scatter, and we can have leakage. So when you look at this top group, you can have some that get absorbed, you can have some that leak out, and then you have some that scatter down. And in this particular case, it can scatter to like number 15, it can scatter to number 14, everything including all the way down to thermal. So you come up with a term for each one of these. So in this case, absorption would be 1, scatter would be 16, leakage would be 1, fissioning is 1. So you're going to have 1, 2, 3. You're going to have 19 terms on this side. And this is looking at the change of the neutron population in group 16, the very first one. Then you're going to do it for number 15. The same type of thing. Production minus loss. In this case, some of the thermal neutrons created,
Going through that explanation for me.
well, you asked me what time it was. I told you how to build a clock, so I didn't really need to do that.
I appreciate that. That's all right.
Let's take what we have and let's see if we can apply that. Okay, let's take any fuel moderator mixture that we have. Up to this point, no matter what we've had, we've been able to calculate K infinity, and we've been able to calculate buckling. Both of these are due to fuels and moderators. When we developed the expression the other day for leakage, we ultimately came up with an expression that said we said this is the general diffusion equation. So this is good for any fuel and moderator mixture. We use the del 2 operator to tie in reactor shape. So no matter what I give you for fuel and moderator mixture, this is the governing general diffusion equation. No matter what shape you're asked to put it in, a cylinder, a sphere, a cube, whatever it is, this is still the expression that covers everything. And then what we do is we're going to use this del 2 operator to modify this to whatever we're interested in. So let's go back to the general diffusion equation. And now I'm going to look at an infinite slab.
Is there a definition for the del squared?
The del 2 is actually going to be a function of the shape that you select. I'm going to go through that in just a second. Okay. So let's say I go for an infinite slab. An infinite slab, if I look at it, I can erase this over here now. This is the plus x direction. This is the minus x direction. This middle section, the red is showing up. Let me shoot to blue, maybe. You never know which of these are going to work. This is your fuel and moderator mixture that's put into an infinite slab. So the physical shape is anything inside the boundaries. Y goes from minus infinity to plus infinity with fuel. Likewise, Z goes from minus infinity to plus infinity. Are you ever going to have a reactor where in 2 dimensions the fuel goes to plus or minus infinity? No, but it's an easy way to learn how to use the diffusion equation. When you do this, this distance is x sub g, where x sub g is the physical dimension of the mixture. And I particularly notice is this point, which is plus x sub g over 2. This other side is minus x sub g over 2. This is your origin, which is 0. When you put a fuel and moderator mixture in here, it will generate a flux. The flux is generally, so we'll have the flux equation. So we're going to take the general diffusion equation, to a specific diffusion equation based only on shape. Then we solve that specific diffusion equation using initial and boundary conditions. That's sort of in words what we're going to do. So let's look at that. So let's take the general diffusion equation, and then we're going to correct this for a specific shape, and then try to solve that. So for an infinite slab, only variable is x, because the fuel goes to plus or minus infinity for y and z, so it does not change. So my del 2 operator becomes dx2, because the only variable is x. So this equation then becomes d2 flux dx2 plus b squared flux equals 0. So this is the modified general diffusion equation to become the diffusion equation for an infinite slab. Now, I don't know how good your math is or where you stand in your calculus, but if you solve this, the solution to this, let me erase this. So we've got it to this because it's an infinite slab. So if we go to solve this, the solution becomes the flux. These things drive me crazy. And if you want to follow along on this, we're doing this on page 263. So the solution to this is A1 cosine of Bx plus A2 sine of Bx. We're now going to use this for initial and boundary conditions to solve what has happened. Okay. We know that if we take the differential of x with respect to x, which is the slope, we know the slope is exactly 0 at or on the center line, where x is equal to 0. So this is my center line. This is where flux max is. That's also that. So if I take partial with respect to x of this, then I have the flux dx is equal to minus a1 b cosine of dx plus a2 b sine of dx. And now I know this is exactly equal to 0 when x is equal to 0. So if I let x equal 0 here, the cosine of 0 is 1. So this becomes minus a1b times 1. The sine of 0 is 0, so this becomes ab times 0. And using logic on this, if this is 0 and one of the other answers is 0, then it means either one of your arbitrary constants of integration is 0 or buckling is 0. We can't have buckling equal to 0. So that makes one of your constants go away, and you end up with the flux is equal. But if you have, I'm just going to, buckling squared we had was 0.0423 centimeters to the minus 2. So if we take the square root of that, buckling is equal to our 0.206 centimeters to the minus 1 is equal to pi over x sub 0. So x sub 0 is equal to pi divided by 0.602. The answer is going to come out in centimeters. So that is the dimension where the flux goes to 0, that total width. Then we can relate that back to the geometric dimension. by that little d that we had, which is this distance between the geometric boundary and where the flux goes to zero. They show you how to develop that, but that is equal to 0.71 divided by macroscopic cross-section for transport. We calculated that when we were finding buckling for our shape. As soon as you have that, you know x of 0 is equal to x of g plus 2d. So we just calculated this. Now we have this, so you can find out that geometric dimension. I'm going to pick up on that hopefully on Monday, definitely on Wednesday or so. And just let me show you one final thing before we go today. When we go to take this to a different shape, we know we're always going to go back for our general diffusion equation. What we just did was for an infinite slab. Suppose we had a three-dimensional rectangular solid. We know that flux is going to be a function of x, y, and z. So that means we have to find a del2 operator to accomplish that. If we do, this del2 operator becomes so then we substitute our del2 into this because this is the mathematical function acting on our flux. So this becomes we then solve this equation to come up with a function of flux. And then we use boundary and initial conditions to narrow that down like we just did for the infinite slab. So I'm going to continue this lecturing hopefully on Monday. So just to go through very quickly, I will be here the next 3 afternoons if anybody wants to call me to see me about registration, the waiver, anything about anything. On Monday, well, actually Sunday, Monday, and Tuesday, I'm involved in a virtual accreditation or reaccreditation of a college in South Carolina. I do not have back my final interview schedule for Monday. It looks like right now, for the tentative schedule, that I'm going to have available on Monday, I'm going to be tied up except 2 to 2:45, so that might change. So I will send you an email on Friday afternoon. And I'll hopefully know then exactly what my schedule is going to be on Monday. If it turns out I have this gap in my interview schedule from 2 to 2:45, I would like for us to meet Elron 2 to 2:45. And when we do meet, I'd like to get your nuclear material science quiz ahead of time. We will go over that. And then I want to spend the rest of the time catching you up on reactor theory for the infinite slab and looking at that application in the book. And then I'm going to give you a quiz that'll be due on Wednesday. If on Friday afternoon I find out that the entire afternoon on Monday is wiped out with interviews, they've scheduled other things for me that I didn't know about, or they moved people around that I didn't have any control of. If this goes away, I will let you know that in the email, and then this quiz will be due on Wednesday instead of Monday. And we'll go from there. Any questions on what we did today, or tentatively what the schedule is? I have I just checked in the meantime, so Robert, Andrew, and Conrad agreeing to go to 12:30. I checked and that is open, so you are officially in that. I will have the registrar move it over. You don't have to do anything. I still need one of the remaining 5 for Thursday morning's lab to agree to move. And for the lab section, I had Ryan Nobles agree to go to Tuesday. So I'm still looking to hear from Evan, Anthony, and Ryan McNally by Friday. And this is for the UI lab to move from Friday to either.
Professor, I'll take Tuesday. This is Anthony.
Okay. Okay. So that still leaves Ryan and Evan. So probably for you, I'm going to probably have to put one of you on a Tuesday and one of you on a Thursday. So hopefully you'll come back and that'll balance out. If not, I will do it by Friday.
I had picked Tuesday.
That's right. Okay. Okay, so you're Tuesday. So Evan, you go to Thursday.
That's fine with me.
Okay, you're all set. And again, as soon as I get what those labs are, the directions, I'll also send you a copy again of what I expect the labs to look like when you report back for your reports. Again, I'll be here today till at least 6 and probably later. Same thing tomorrow from 4:30, probably 7. And then I'll probably get in about 1 o'clock on Friday and be here till at least 6, maybe a little bit later. So you only have the one quiz due. If you can, for the reactor theory, go back through and review infinite slab. And then we're going to finish up that application, and we're going to look at rectangular solid. I'll go through very briefly how you would approach doing something like a sphere, how you would do a cylinder. In each case, what really changes is that del 2 operator. And then you have to know how to be able to solve that equation that it generates. Thank you for your time today. Good luck with Professor Lance, and I'll catch you later.